my slide. And okay. And it's nice to see so many friends and colleagues in the audience. I'm going to tell you today not much about science, not about my own science, mostly about our liquid spectrometer at NSLS-II, the Beamline, with mostly science of others. I just want to point out that the Beamline is really a team, Honghu and myself, we're both local contacts. And this is not the normal type of talk I give. I mostly give a talk on science. This talk contains some laundry as how to make a liquid spectrometer form optimally. So let's see if we can advance the page. Okay. So for those who haven't been to Brookhaven, Brookhaven is on Long Island. New York City is over here. By train, it takes, an hour and a half or so to get to New York City from the nearest train station. Here's NSLS. You can see we have lots of rings. This one you can see from the air if you're flying over. That's the Rick ring. Over here is the old NSLS-II, which closed in 2014, now a computer science center. Close by, we have the Center for Functional Nanomaterials. It's not next to our new NSLS-II as it is next to your synchrotron. And there are 5 sort of office modules in between. So the first light was in 2014. It's smaller than APS, is 792 meters in circumference. It's lower energy, 3 GeV, which works up fine to about 24 kV. We're now operating mostly at 500 milliamps. We have photons coming out from IR to hard X-rays. We're a little bit probably better in the soft. There can be sort of 70 simultaneous hutches. Our first light was over here, and here's the ring. And you can see it's not fully developed, sort of half developed. Here's our Beamline here, and we have a very nice large chemistry lab close by, which is different than at the APS because it's shared for the whole ring. Mark alluded to I was on early on, but these 2 fellows were on before me. And really, this is a tribute to Jens Nielsen sitting in front of the computer, looking at the camera, and Peter Pershan. And this was probably about 45 years ago, very early on days at Doris 4 in Germany. So we owe a lot to the ingenuity of these 2 guys. So we have a long history of liquid surfaces. Peter started building a liquid spectrometer even before I got there. When I was this postdoc in about 1985. We got going in about 87, and X22B was different. It wasn't, we didn't have to give out so much, only 25% to outside users. And so we really got to do a lot of science there. But it was time to build a new ring, and we put a proposal early on for SMI before the ring came up as part of the next project, and it got great reviews. Mark and some others on the line were involved, and there was supposed to be a liquid spectrometer in the front hutch. Unfortunately, this never happened, and it was curtailed in 2015. Well, I moved over to NSLS in about 2016. We wrote a proposal for a canted undulator. That got great reviews, but it was never funded. So we ended up taking this existing hutch shown over here. We took parts from the old liquid spectrometer we had built at the APS at 9ID and the one from Brookhaven, and we built this in the hutch over here. And I want to thank people like Mark and Philip Fontaine and Oleg, who were on our review committees and provided a lot of very good insight over the years. Okay. So here's our instrument. Here's the instrument before it was fully built, and some of the members of the team stepping on this big piece of granite. That piece of granite over here, there are 2 pieces of granite, actually. One is for the deflector, which it can be moved forward and back. The advantage of that, you have to move this pipe out of the way, but you can do that is that you can get a longer lever arm, and you can make your sample farther from the wall, because the wall is just behind over here. So, but we typically run with a lever arm of about 700 millimeters. I'll show you more about the instrument over here, but the point is it's on very large pieces of granite. You can see this is not the type of instrument at the APS where the sample is attached directly to the deflector. It's on a separate rails, and there's geometry involved to position everything correctly. It works perfectly fine, though. I think we figured out Euclidean geometry a while ago. So here's a picture of the engineer, Daniel, who designed the instrument. He did a very nice job. We worked with him for many years. I'll show you some parts from here. So this is recycled from the APS. This is a Huber 4 circle, and it has an elevator underneath. And this supports the 2 theta arm for the output stage over here. And we have slits and monitors and stuff up front. More recently, we've added CRLs at the front, and I don't have it in the drawing. And then this is the sample stage here, another equivalent elevator that can support up to 200 kilograms. Is all very nicely aligned because this rotation has to be in the center of this rotation. And over here, we have a very large 2 theta arm with detectors as far as 1.5 meters out for SWAXS. And I'll show you on the top view of this, you can see this is the SWAXS detector 1.5 meters out. This is the sort of typical arm that for the, like you have at Argon and we've had before, for the a normal reflectivity detector. And now we have another detector that we can move in close. And all you have to do is these all have different zeros, and the program knows what the zero, and if you pick this detector, tell it to go, it'll go to its corresponding zero. And even more complicated, on top of this, we have Soller Slits. So we actually have 4 2D detectors working in this beamline all simultaneously. I just want to say, if you have questions, please don't hesitate to ask. So we share this beamline with the one behind, which is over here, which is a small angle scattering line. And when we operate, we use the same focus, that we use the same horizontal focus. And the horizontal focus we can adjust, whether it be at the sample or somewhat before the sample. We actually usually have it much earlier because it also goes through the CRLs, and it's a little bit complicated. I'll just show you the final output. We started using actually these mirrors over here. There's a vertical focusing one with a bimorph and another one to make it parallel, but we could never focus more than 30 or 40 micrometers. 30 was on a good day when we slid it way down. And we weren't very happy with that, and we spent weeks trying to improve it. The other problem, it vibrated up and down. And Mark and others were very involved in suggesting we get rid of that mirror and just put in CRLs, and that's working great. Now with the CRLs, we have a knife edge scan over here that's blocking the beam, and that corresponds to as small as 6 micrometer beam at the sample position. We actually don't even like to run that small. We typically run with 12 micrometers. With the bimorphs, I said it was much better, and we have much better stability. And the horizontal focus, it's a bit complicated because we have both the mirror and the CRLs, because this is a 2D CRLs. And to get around that, we actually use a miscut crystal, and we can get a beam 300 to 400 micrometers. And that's the size we like because there's spreads it over the sample a little bit more. So in building this instrument, we had to make sure this is 25-year-old Huber goniometer. How good is a 25-year-old Huber goniometer? Probably as good as a new one. So we actually measured with an angular interferometer that says if we go 1 degree, does it really go a degree? And we actually calculated the offset, and the wobble was 0.015 degrees. And you'll say, that's a lot of wobble. But it turns out over the range that we're doing, if you do a linear fit, because we know its behavior with this, that the wobble is quite small. So it is quite, with corrections and all, it's quite linear. We don't even add these corrections. We know it's working well because we have a slit on this detector arm afterwards. I don't show it here. So the beam gets deflected and there's a slit, and we have to move this downward. And if there was nonlinearities in the chi-circle or this, we couldn't fit this tracking wouldn't be so good. But this tracking is within a couple of micrometers, and we consider that excellent. So we certainly meet the specifications. I don't really want to go this in detail, but we actually ended up putting the incident flight arm over here, all in vacuum. We've added some other stuff into it. We have ion chambers outside. We have some beam visualization that we can transfer. We also have a Diamond BPM for tracking, and we've played with it some, but the tracking is so good without it, we really aren't using it, and we may use that for a monitor of some other point later on. So we have to, when we tilt down, we have to Bragg reflect and continue to Bragg reflect. And here's, if this circle has to be perfectly perpendicular to the incident beam for the alignment, or very perpendicular. If it's misaligned when we tilt, when we do phi scans, the phi scans are going to drift outward. And when it's well aligned, we can go to very different alpha, up to 4 degrees, and there's no change here. So it's very good. And this is within, the tracking is within 2 10,000ths of a degree. That's sort of typical to sort of what we do the RMS. So this is all excellent. So it tracks perfectly. We don't have any problems with that tracking. But we did, in using the old instrument, we did encounter a problem. And this problem, please interrupt if because I know that way I know you're there. Have any questions? No questions? No comments? Everyone's muted?
We're listening.
Okay, good. Okay, so what we have to do is, this is the sample elevator. We move the sample elevator up and down, and we want to see if it goes to the position we tell it to go to. And then we look at the deviation in the sample elevator with an optical interferometer. And you can see the blue line that it has some periodic behavior. And we know what that periodic behavior, it's about 1/100th of an inch, and that corresponds to 1 revolution of a motor. And this is sinusoidal, and we put it in to correct for it. It doesn't work perfectly. So this amplitude of this is something of the order of 3 micrometers. And it turns out that this was at first giving us problems. When we had the mirror in place, you'll see we were seeing some modulations below the critical angle, and we shouldn't see that. And that was coming from the fact that the beam spreads a little bit too far out with the larger beam on the sample, and we move up and down, the beam is moving sideways a little bit, and we see this behavior. And so previously, when we had the regular mirror, we had like 30 microns, and at sort of half the critical angle, it would be spreading on the sample about 86 millimeters. And we could only really use like 35 millimeters flat part. So it was really critical to have a 6 micron beam, which we don't typically use. We prefer 12 microns. And when we do that, sort of at half the critical, it's spreading out over at the energies we're working at about 34 millimeters. When we get to the critical angle, it's close to just 17 millimeters. So that works very well. And when we do that now, when we look at the X-ray fluorescence, it's all nicely behaved below the critical angle, and we don't see those modulations. Okay, I'm not going to say much about Bluesky. That's our software. We no longer use Spec. Spec isn't banned at Brookhaven, but they spent a lot of time developing this, and there's some very nice features. One feature we use is we have, as I mentioned, 4 different detectors, and they have different offsets in 2 theta or in output height. And we have a command, for instance, set mode, and we can pick like X-ray reflectivity, solar, or any of these, and it picks the detector and it knows what the offsets are. So everything works perfectly. For instance, if we then do a sample height scan, it knows what detector to choose and what region of interest. So you don't have to change your commands for instance, of setting sample height, depending what mode you're in. And we also have a mode for X-ray fluorescence. RE, by the way, stands for run engine. The disadvantage of Bluesky is it takes about twice as many characters to type in to get things done. spec was very compact. Okay, so these, we all know, I think the audience all knows what X-ray reflectivity is. I'm just going to show you, we use this detector over here, which is 1 meter out. It's I missed a slide, I'm sorry. For the reflectivity setup, it's over here. There's a detector, here's the flight path, it's rectangular, and there's this small detector. We have a small cooling fan on the top. This is this very small lambda detector. It's only has 512 by 512 pixels. It's about an inch on the side, but each pixel is very small, 55 micrometers. And we can actually have about 330 pixels per millimeter squared. So when we use a millimeter by a millimeter region of interest, it's spread over more pixels, and that means we can go to higher counting rates. And we also get better resolution. It's about even twice that of the Eiger and much higher than the Pilatus. The other advantage of this detector, it has gallium arsenide on the top. And we often, if you use silicon, this is the efficiency, because when it penetrates deeply, the efficiency goes way down. So when you're out at above 20 kV, the efficiency is like 20%. But with the gallium arsenide, it's still very high efficiency at the energies that we work at. And that's an advantage. And that's why we picked this detector. We picked it over the Eiger. Okay, so here's, we have different modes. Most users are interested in X-ray reflectivity, where we have to vary the incident angle. This is for a DPPC monolayer. We go to some pressure over here. We see the reflectivity. We get 10 orders of magnitude of dynamic range. We can go up pretty far out. Sort of, that's where we start seeing error bars at 0.7, sizable ones. And then we can analyze this using the master formula to get the scattering length density. Nothing new over here. And over here, that's the detector on the side. Okay. So, why did I lose one here? Well, I lost, did I? I deleted a slide I was supposed to have. Okay. What I deleted is we have a setup for doing solar slits, which is over here on top, and somehow I don't see that slide right now. Maybe I'll find it later on floating around. Okay, so yeah, I'm missing a couple of slides. Okay, well, here's this new detector over here where you'll see it in the data. This we just put in. This is a detector on the side. It can go close. It has a very large range in Q space, over 1 inverse angstrom of Q space. This was for a cough that was done recently. This detector just got installed in January when we got a new 1M detector back here. Here's a line cut through it, and it's very nice for doing survey work. Of course, the background is going to be a little bit higher. And here we had a PFAS monolayer, and you could just see the PFAS, the Bragg rod of the PFAS monolayer. So this is very fast and useful for survey work. We have Grazing incident angle X-ray fluorescence. The detector comes above. Here's this type of sample chamber we use often with these little Teflon troughs. This fits inside this slot over here. And when we move this back and forth, because we can have 3 or 4 samples in here, this detector stays fixed. This is a vortex detector, and you can see over here some fluorescence, and this is the critical Q. And if you have scattering below, that means it's on the surface, and over here, these other lines are not. And we can actually see fluorine as well. Often we have to put attenuators on because the bulk Compton scattering is very strong. Okay, just to show you, we have a trough. This is a Kibron trough that we bought commercially. We had modified help of Chen Chen. We actually shortened it, which worked out well. We have a lightly different design here. All our connectors come out the bottom, and this big plastic piece, which is the cover, can easily be lifted off. It's also much easier to modify this because there's no electrical connections or anything coming out. So it's heavy, and this hangs from this rod coming up here. It goes higher up, sort of above the vortex. Okay. Let's see how I'm doing time-wise. I think I'm going to stop and show you what I deleted accidentally. So I'm going to, sorry about that. Let's see if I can find, must have done that recently. No, I don't know where the backup is. So, okay. Well, trust me, we have a very nice setup, and you're going to see this in the data when we get to it. I don't know what happened. Okay. Okay, so I'm going to just tell you a few examples of some of the experiments that were done here, some from our group and some from outside groups. So I'll talk about branch fatty acid monolayers, PFAS monolayers, pseudo X-ray reflectivity, where we can do direct comparisons. Let's work with Chen Shen. PEG encapsulated gold nanoparticles from Vaknin's group. Mono ion specificity near protonable surfaces. That's Pulak's group. And there's another one I forgot to mention here from Charles Maldarelli and company. Okay, so this work is with Guanqi Yuan and Sushil Satija. This is a very interesting molecule because it's like a normal fatty acid, but the end group here has two methyl groups, so it's kind of bulky at the end. And if you do an isotherm, and we do this in a solution containing ions of let's see, it's a strong divalent ion, and you can see that the isotherm comes up also like arachidic acid. With this, it comes up very fast with these ions. This comes up slower, but it all sort of happens at 25 angstrom squared. Anyhow, there was some previous work transferring to a solid surface in 2020, and they could see that there was nanostructure on these surfaces. These are Langmuir Gibbs films. So we're doing this directly on the Langmuir Trough, and you can see a very nice GSAX pattern with our detector. And this has a hexagonal lattice of about 51 nanometers. But we also can do with our Soller Slits the GWAX setup, and we see actually some sort of coexistence, it's not quite a Bragg rod, it's sort of tilted because the monolayer has some continuous tilt, it's not sort of fixed. But we also see some spots over here from this rectangular lattice that's kind of weaker, which is interesting. So we have this idea, sort of a proposed model, because you can see if this is very bulky, some of the molecules you can tilt, and if you tilt, if you tilt, you can sort of move them to the side, but they also sort of can move up and down and make more room at the top. And so we have something like that.
So Ben, so those rods, which are out, those two, they're very narrow in QZ. I mean, is it because the structure collapsed?
We see that it's possible, but we see that over a range of, you might be right, because it's very sharp in QZ. So that it could be, that's a good point. Thank you. That could be. Yes. But even we observe this at fairly low pressure, but because of this isotherm, maybe it collapsed earlier. I don't know. It's not, it represents a small fraction of the overall intensity. It's just a mysterious thing, but it's not the predominant phase. That's a good point. It could have collapsed. Okay. So what I want to show you is we look and see how the pressure, we change the pressure from 5 to 35. And as we do that, you can see the G SWAXS, and that's changing. And you can see that this peak is shifting over, and we can get the position, and it goes from 60 nanometers down to about 50 nanometers. So as we're compressing it, these nano features are getting closer together. And it's also, we know from the X-ray reflectivity that the roughness is also increasing because it's getting much rougher. So this looks like a normal one, and this roughness, it comes way down. And that means that the peak to trough height is getting much larger. So we also looked at a range of different mixtures, but I'm just going to show you one. This is if we mix it with arachidic acid. And instead of forming a hexagonal phase, it forms a linear phase over here. It's sort of a 1D structure. And what's very interesting, as we squeeze this structure, this length gets farther apart. So this stripe separation goes from about 100 nanometers up to 200 nanometers. And when we do that, there's really little change in the reflectivity. But reflectivity is when you have such a large structure, you're not really looking at the coherent average over the whole structure because of your coherence length. And that's going to do very strange things to the reflectivity and may actually explain why the reflectivity gets a little bit stronger as we squeeze it. So we have a lot of data on this, and we're in the process of writing up a paper. This is earlier stuff. I didn't show you the most recent. So this is pretty recent stuff. This is working with Stony Brook University. We have a very active program looking at all types of PFAS monolayers with X-ray reflectivity, GWAX, and also fluorescence. These are common sisters and brothers of what we look at normally. Here's the fatty acid group. These chains are shorter. This is PFOA, which is only 8 carbon. It's totally fluorinated. Often, I think Benoit and others, maybe for her thesis, they looked at some semi-fluorinated ones. They had like 2 hydrogen ones at the end and were much longer over here. Anyhow, this is sort of very relevant because PFAS remediation is a major societal issue, and you can bubble and bring PFAS up to the surface. And there are various additives, cations, and other things like relatives of CTAB that can have a big effect on this. So we can study this, and the previous only measurements of what was going on are thermodynamic measurements. Anyhow, this is sort of what reflectivity curves look like, normalized reflectivity curves. This was very idealized, what the reflectivity sort of looks like as you're changing. So what we're doing is we're changing the concentration in the bulk. This is very weak, 25 parts per million. This is 2,500 parts per million. And you see as you go to higher concentrations, you actually get more on the surface, but then the surface tension goes down, and actually the reflectivity goes down because of that. We vary the bulk concentration. The other thing we can do is, as I showed you before, we can do GID measurements, and you can see the background is high here, but you can see a peak here at 1.14 inverse angstroms over here. And that's from the in-plane order. And from this, you can get the area per molecule, which is like 34.8 angstroms squared. This thing is more liquid-like. Well-packed monolayers of fluorinated ones are 28.5 angstroms squared. And so this is the work of a graduate student, Andrew Wright. So this topic here is pseudo-reflectivity and really deserves a talk on its own. And I hope someday you'll get to invite Chen Chen to give this talk. So it turns out that we can measure, normally we measure the reflectivity by varying the incident angle. But you can get to, if you can get the diffuse scattering from the reflectivity by coming in at small incident angle below the critical angle. And for instance, you get this sort of features over here, and then you can measure at various 2 thetas and measure what this reflectivity over here, it's not reflectivity, just what we call R star. And what we do is we measure this R star, and we know the math for capillary waves and what the diffuse scattering is, and we can then calculate what the reflectivity would be on axis. It's what we measure over here divided by this number R. And we know how to calculate that number R over here. So that tells us, if we're doing it right, that we can measure the reflectivity in a single shot off axis. And here is a comparison. And this is not a comparison. This is for some monolayer over here, and it shows you. I'll show you more. So this is some expression for R. I'm not going to go into the details of this expression, but it depends on how much you're integrating in delta beta to theta. It depends on this number eta, which relates to the temperature and surface tension. But this is in this paper over here that was published last year. So if you're interested, please take a look. I just want to point out that there was much previous work in the field, sort of the diffuse scattering and bending rigidity. I don't have time to go into it, but there was some very pioneering work at the APS that was published in 2011 that used this technique in a slightly different way. We convert it to reflectivity slightly differently. Okay, so to make more easy comparisons. So how well does it work? Well, this was work done at Petra. Normally, we only take water reflectivity out to 0.8. Here, what we do is we take it with different 2 theta offsets, and then we use this formula over here to calculate the reflectivity, or R over RF. And you can see this is the results of previous water work done by Pershan and others. And this is the results over here, and there's very, very good agreement. So that really tells us that this formula is working well for something like water. And we're actually getting farther out. So what happens if you put a monolayer? So first, we like this CTAB monolayer. It's a Gibbs monolayer, so you don't have to worry about burning up the sample as much, and pressure changes because it comes from underneath. And so this comes to the surface over here. And what we've done here is we've compared, this is from P08, this purple curve, so that's pseudo-reflectivity there. And we also have pseudo-reflectivity at BNL and regular reflectivity at BNL. Not perfect agreement, but overall pretty good agreement over here. So this seems to work well for soft liquid films that don't have bending rigidity. Something that's sort of small and squishy is like this. But when you have long molecules like this, they can suppress some of the capillary waves, and you have to take that into account, which we have done. And I don't have much time to go into much detail. But I just want to point out that you can also look at the diffuse scattering in this direction over here. So we're doing a scan along here, okay? And when you do that for water, you can calculate it. This black line over here is for capillary waves, and you can see the diffuse scattering follows capillary waves, nothing new. For DPPC, which has bending rigidity, that's the capillary wave lines over here. It falls below it. And we actually have this other model, which we call the extended capillary wave model, that includes bending rigidity, and you can fit it well. I don't want to go into it. These are some of the expressions, and this contains a lot of other variables that I haven't defined here. And we're working on getting this paper done. Chen is on the line, so needling him we need to get back to it. Okay, so when we do this at, very important, we can do the measurement of these pseudo-reflectivity at our beamline over here. That's the red curve over here. This is from OPLS. And we also then take the regular reflectivity on the same sample, and you can see there's very good agreement. We could have taken a few more data points. It was sort of sparse, and this has a medium-high bending rigidity. So what this is really telling us that we think we understand how to properly include bending rigidity. Now, here's another one. Going back to the PFOA, we can only get out to about 0.6 inverse angstroms using normal reflectivity because the surface tension is fairly high, and the signal was falling. But with pseudo reflectivity over here at our beamline, we can go. No, this was probably in Germany. We can go much higher. We can go to much higher thing. And the point is over here, I asked the graduate student to compare the two, and he got it right the first time. And you can see that there's very good agreement. And we reached, for those who know what eta is, eta 0.6 over here. And this is what I was showing you before. The area per molecule was 34.5 angstrom squared. Okay, so when we do this, we add OTAB to it. So we add a cationic surfactant. The surface tension is even much lower, 16 millinewtons per meter. And when we do the GID, this is the peak over here. It's 29 angstrom squared. And we see another feature over here because this is not, there's no cancellation from over here. So this is coming from the 100 peak. Okay, so here's some work from outside groups. I think you all know David Vachnin. I don't know if he's on the line or Wenchi, but they've done a lot of work, beautiful work on gold nanoparticles. These are encapsulated with PEG. They can vary the molecular weight of the PEG, and they can vary the size of the gold. And they take X-ray reflectivity. This is normalized X-ray reflectivity. They don't have to go very far out, only out to 0.3, and they can fit the data and see that this is at the surface. They also do, this is the type of GSAX data we get, and you can see that this is beautiful data over here. It's easy when you're a little easier when you're using gold, and you can see these peaks correspond. It's hexagonal because they're all in the right position. And this is form factor over here. So you can see various changes in how, under various conditions, how the scattering, these are line cuts. And so when you go to longer PEG, you can see the peaks move smaller in. So they've done, I think there's 5 papers from this group at our Beamline. I'm only going to tell you about the first 2. This is kind of interesting. They didn't make the particles identical, just like the PFAS, when we have 2 particles over there. You can see it's not a centered unit cell, and it's a binary system, and it's this AB system, and it turns out it has this √3 by √3 cell, which is much larger, which has both particles in there. And you can look at the data over here, and then you see the emergence of a new feature at lower Q from this much larger unit cell over here. So they've done a lot of work in this, beautiful work in this field.
But did they go much farther in the angles in order to see the scattering from the gold, from the lattices?
No, to my knowledge, they haven't done it. If one of them is online, I know that in some cases, the gold lattices are they align. This is, I think you would need a much smaller encapsulation. I think they're going to be randomly oriented here. In some cases, you can see that when it's very short, I think if you put thiles on the end, you can see that the gold lattice has a preferred orientation.
Yeah, well, I haven't done anything with the PEG, but with some other particles decorating and that work was never published. But we have seen a strong texture. So the gold wants to lie on the surface or the gold nanoparticles likes to lie in the surface with a certain orientation.
Yeah, I would believe that, but it has to be thin enough. These, I think, are too thick for that. You won't see it.
Okay.
But if you went with a square particle, with some of these coatings, you might be more likely to see it. Okay. This is recent work from Pulak Dutta. I could only find an old picture of Pulak with his student Yan Lin. Well, I think she's been happy to come out because her thesis fell between sort of COVID and the APS shutting down. So she's been out 5 or 6 times. They do X-ray fluorescence data from this, and they can see what the ion concentration is. And in this case, they're using a cationic surfactant, octyl amine. And what they're doing is they're varying the pH and they're varying what the ion is over here, and they can measure the coverage. But if their pH equals 4, you can see that independent of the ion, that the coverage is about unity. But now, when their pH equals 5.7, the coverage depends very much on the pH. And this sort of is related to what the pKa value, which is about 5.5 at the surface. It's very much higher in the bulk, and how it's protonated. And I don't know all the details, but they have a paper which this is discussed. Okay, now gosh. Okay. This is enhanced rare earth element recovery. They're using a protein, this Bluta lanthanum binding peptide, and they can vary the concentration of this peptide. It's called GA over here, and they do X-ray reflectivity at this interface. So they have beautiful X-ray reflectivity. And you can see these peaks is from the monolayer. I think this is with the over here. It has higher concentration of GA and less over here, and get beautiful fits. And they can get the profiles out over here. And this is where this binding protein fits over here. So it comes up to the surface, and they can see, depending on, and they measure X-ray fluorescence over here. And you can see now we get very nice data below the critical angle. So this is the bulk scattering over here. So there's a lot in solution, and you can see this part is coming from the surface, and they can analyze the data over here for the terbium lines, and they can see how this protein helps bring the rare earth elements up to the surface, improves it, and has some specificity. Okay, this is the last one. This is Honghu Zhang, who I work with now, but he's very accomplished in this field. He had done his beautiful PhD with David Vaknin, and then worked with Oleg Gong at the CFN, and happy to work with him now. They looked at peptoids. These are sort of chains of proteins that are attached to the surface. You can modify this. They know this is a very compact layer of proteins on this gold nanoparticle surface. They can see that it comes to the surface. They do it in different conditions: sodium chloride with a protein, and then with the protein with PB. What's PB? Peptoid, and then with the sodium chloride. The point is, you can see this beautiful reflectivity over here from the gold nanoparticles, and you can get the electron density over here. They also see that they do GSACS, and they can see over here that this is just water for background. That's our beam stop, and just sodium. I guess it's sodium chloride with the nanoparticle, and under various conditions, and they can see that it's forming a hexagonal structure over here. So just to tell you about, we've had many user groups and program status. First, we prefer to run at 14.4 kV. It's a lot of work for us to change the energy and realign. So unless there's a strong reason, we stay at 14.4 kV. About 20 individuals have submitted proposals. Of course, some groups have more than one scientist, but so maybe 15 individual groups. 15 individuals have received beam time, so there are about 5 out there. We keep on submitting, or some of them do and haven't gotten time. We have about 15 days of time per user cycle, and there's 3 cycles a year. So we have tried to run 2 days per run. That's very challenging on us and the users, and we can get 7 users in. Normally, we prefer to have 5 users per cycle with 3-day runs. Nobody has ever had a 4-day run. So we just don't have the time. We try to keep a couple of days of commissioning per cycle, because we have to realign it every time, every 8 times. We run for like 8 days. And we leave a few days of science for the Beamline scientists per cycle. But we're way oversubscribed to a factor of 2. I think some of the users will be happy when the APS comes online. It's a very flexible setup, and we try to continue to improve the efficiency so that now with multiple cells, with multiple pressure measurements and movable barriers, so that we can that our users can get more science done in a short amount of time. So thanks for your attention.
Yeah, thanks, Ben, for a nice